Hello and welcome to this talk on Introduction to Molecular Dynamic Simulations. My name is Siddharth Gautam and I work at the School of Earth Sciences, the Ohio State University that is located in Columbus, Ohio, United States. Just to help you locate Columbus, on the world map you have on the left India and United States highlighted. Within United States on the right you can see there are different states, and one of them is Ohio, which is located close to the Great Lakes in north. The capital city is called Columbus, and Ohio State University is located in Columbus. This talk is divided into three different modules. We'll start with the first module, which would give a very layman's introduction to molecular dynamic simulations. Then in the second module, we'll get a bit more technical and we'll see how to carry out an MD simulation, which is something like making molecular movies. And in the third module of this talk, we'll talk about how to obtain some useful quantities calculated from MD simulation data, or in other words, how to make sense of the molecular movies. So we begin with the first module, which is a layman's introduction to MD simulations. So in this module, we'll be talking about these topics in particular. We'll start with talking about what is a simulation in general, and then we'll talk about why we need simulations after all. We also need to talk about what is the need for molecular level information, and then we can talk about some experimental techniques that can provide this molecular level information and their limitations. After this, we'll then be able to talk about the need for molecular simulations. And after this discussion, we can then go and take a brief overview of molecular dynamic simulations. And finally, before closing, we need to distinguish between two different types of molecular dynamic simulations, that is Ab-initio and Empirical MD simulations. In this workshop, we'll be focusing on Empirical MD simulations. We'll see later. So, what is a simulation? Oxford Learner's Dictionary defines a simulation as a situation in which a particular set of conditions is created artificially in order to study or experience something that could exist in reality. These simulations can be real-life simulations, or they can be simulations performed on computers. We'll see examples from both these cases. Talking about real-life examples, we have seen children playing, and indeed when we were children we also played games like playing doctor. These games are in a way a simulation where children pretend to be doctors, or sometimes they pretend to be patients. Another example can be movies in which actors play different characters and they try to simulate different events in one's life, fictitious or real. Yet another example of a real-life simulation is a crash test of automobiles. So, for example, automobiles conduct fake accidents with their motor vehicles with dummies sitting inside. The idea is to see how these dummies can get damaged in an accident, and a similar fate can be expected for the drivers and passengers. So in all these real life simulation examples, there can be a lot of imagination and creativity For example, in kids pretend plays, there is a lot of imagination and creativity. Whereas if you consider crash test, on the other hand, there is more accuracy with respect to laws of nature rather than creativity. Here are some examples of simulations done on computers. So, for example, one can simulate the collision of two galaxies. For example, here you can see time frames from the simulation of collision of two galaxies. This work was published in Nature in 2005. You can see the two galaxies as two blobs. They are coming together, they collide, and after some time come they just merge into two different clouds, gas clouds. Another example can be a flight simulator. They can be games. For example, you can play a game of a fighter plane pilot, or sometimes these simulations are also used for training purposes. Training pilots can use flight simulation techniques. They can sit in a module which can move according to how the plane is moving. In general, this is a combination of real life and computational experiment. Another example can be a much lower length scale example of molecular simulation. So, for example, here you have a picture of liquid water. You can see different molecules of water with these red spheres representing oxygen, and I don't know if this is visible to you, but there are smaller whites or pinkish spheres which represent hydrogen atoms, and then you have connections between oxygen and hydrogen which show hydrogen bonds. We'll talk about that maybe later. The point is, computer simulations can span a very wide range of length and time scales, starting from galactic length and time scales, where the length scales are of the order of 10 to the power of 20 meters and time is of the order of 10 to the power of 16 seconds, which is a few billions of years, to human scale here, and all the way up to molecular scale, 10 to the power of minus 9 meters or nanometers, and 10 to the power of minus 12 seconds, which is also 1 picosecond, that is molecular scale. In fact, you can go even further, and people are making simulations of quark gluon plasma, where quarks are the ultimate subatomic particles that make up neutrons and protons, and gluons are the particles that bind them together. So simulations have been done even at that scale. So now if you have seen enough examples of simulations, both real and computational simulations, the question is, why do we need simulations after all? And the answer is, if you want to understand nature, there have been two traditional ways of understanding nature. First is, you do observations, you observe things, try to understand them, or do experiments, actively perform experiments to understand things. These experiments can be expensive. You need to put in a great amount of effort, money, and time in performing these experiments. They can be very difficult also, and sometimes they can even be dangerous. Another way has been the logical deduction. For example, You can start with basic laws of nature. For example, you can start with Newtonian equations of motion and work out solutions to your problems. You can find exact solutions by making use of logical deduction. But exact solutions are not always possible. There is, since the second half of the last century, there has been a great computational power made available, and this has made a third way possible, that of computer simulations or computer experiments. These are relatively cheaper. You just have to have a computing machine. You can have a laptop or a desktop. They are relatively easier to perform. You don't need to depend upon any other equipment, and there is no danger involved in these experiments. You can even simulate fires, you can simulate very high pressures, you can simulate anything that involves danger, and it won't cause any danger to you. So if you want to have simulations, we are in particular talking about molecular dynamics simulations. So then the question is, why do we need molecular level information? And the answer is, we all know that macroscopic properties are determined by molecular behavior. So for example, intermolecular distances and interactions determine the phases of matter. So for example, if the atoms are arranged in a very regular fashion and quite close to each other, your system is a solid. As the intermolecular distances increase and there is more freedom for these atoms to move away from each other, you get what looks like a liquid. And if this distance, interatomic distances, become very large and the velocities become very large, what you get is a gas. Another example is that of a pathogen attack. So for example, you have a schematic of a coronavirus here, and you can see that this virus has spikes on its body, which is made up of proteins. The way this virus attacks an animal cell is it docks with a receptor, and if you want to somehow make this virus ineffective, one way of doing that is to somehow block these spikes from docking with the receptor. But if you want to do that, you need to understand the molecular geometry, or in general geometry of the acceptor and the receptor, and all these things have to be understood at the molecular level. So you need to have a molecular level understanding in order to effectively find a solution to a pathogen attack. Yet another example is that of gas storage and separation using nanoporous materials. So for example, one of the major concerns we have at this moment all over the world is the rising levels of carbon dioxide in the atmosphere. The question is there a way we can somehow take it away from atmosphere and store it somewhere? And a promising candidate for this is a class of materials which have nanopores. That means these materials have pores of the order of a few nanometers. So for example, here you can see a picture of ZSM5, which is a silicon dioxide material So you can see blue spheres here represent silicon and red spheres represent oxygen, and they are arranged in such a way that you have some porous space left, and some molecules can get trapped in these porous space. So for example, here we have an example of ethane molecule. There you can see some ethane molecules trapped here in this pore, and all these pores. Once these molecules are trapped into these pores, because of the strong interaction with the substrate, that is with the silicon and oxygen here, it is sometimes difficult for these molecules to escape, and this way you can store gases. Another example is that of hydrogen. So for example, we want to use hydrogen as a fuel, but then the problem right now with hydrogen is that of storage. Because hydrogen is a light gas, if you want to store a good amount of hydrogen, you need a very large volume. But if you can store hydrogen in such nanoporous materials, you can compress a great amount of hydrogen in a very small space. Here is another example of a porous material, which is NaY zeolite, and you can see some butadiene molecules trapped into these pores. This is yet another example of a porous material, which is actually a metal organic framework, where you have a metal and some organic molecules coming together, forming a very regular pattern, giving rise to pores. So if you want to have molecular level information, the question is, should you apply quantum mechanics or classical mechanics to understand matter at that level? One way of deciding whether to apply quantum or classical mechanics is to find out the thermal de Broglie wavelength of material in question. The thermal de Broglie wavelength of a material or of an object can be calculated using this expression, where h is Planck's constant, m is mass of the object, kb is Boltzmann constant, capital T is the temperature in Kelvin scale. So at 300 Kelvin, you can work out these constants, and if you express mass in the units of atomic mass scale, then this expression comes down to lambda equal to 4.6 upon square root of mu in angstrom units. And you can very well see that if mu is greater than 4, then this wavelength is always less than 2.5 angstrom. Now just to remind you, mu is greater than 4 for most elements except for hydrogen and helium. So this means for most elements, even for atoms, it is okay to use classical mechanics as long as you are interested in distances larger than 2.5 angstrom. So this means for most practical purposes, for most molecules, you can study their behavior using classical mechanics. Some experimental techniques that provide molecular level information. You can do some scattering and diffraction of particles. You can use X-rays, you can use neutrons, protons, light. Interaction of matter with light can be used to study its properties. Also, interaction of matter with magnetic or electric fields can also be used. So I think some participants in this workshop are familiar with small angle X-ray scattering, and at least one participant is familiar with dielectric relaxation spectroscopy. So these are some experiments that can provide molecular level information. But all these experiments have their own limitations. One is, of course, they are very expensive. So, for example, if you are talking about scattering of particles, scattering of neutrons, to be able to get a good amount of neutrons, you need to have very high flux reactors or synchrotron or spallation sources. Similarly, for X-rays, you need synchrotron sources. These are very large, very expensive facilities. Even for electric fields, you can imagine electric fields might not be that expensive, but then we need to understand that if you want to have molecular level information, you need to have ability to measure these electric or magnetic fields with a very high sensitivity. So that makes these experiments very expensive. Also, all these experiments provide incomplete information. So, for example, if you are using X-rays to study material, you won't be able to see hydrogen atoms in presence of any other heavier element. So, if you have water, for example, mostly you'll see oxygen atoms and hydrogen atoms will be invisible. On the other hand, for example, in neutrons, if you're using neutrons, only hydrogens will be visible, oxygen won't be visible. So each technique has its own limitations and they provide incomplete information. And finally, some of these experiments can be hazardous to humans. For example, all experiments having to do with radiation, be it synchrotron radiation, light, X-rays, neutron scattering, they can all be dangerous to humans. One way of avoiding that is, of course, to do molecular dynamic simulations. What you do in molecular dynamic simulations is, given a system of molecules in thermal equilibrium, the idea is to simulate the motion of each participating atom. So, for example, here you have some propane molecules. You need to simulate the motion of each participating atom here. This would result in a molecular movie over time. So, for example, here at one particular point of time, say starting t equal to 0, your system might look like this. At t equal to 1, the system might look like this. At t equal to 2, the system might once again look like this or some other configuration. And this way, you'll have a molecular movie over time. Or in other words, position of each atom at different times is obtained. This is called trajectory, atomic trajectory or molecular trajectory. This molecular movie can then be studied and average quantities calculated from the trajectories to understand the behavior of the system. And how exactly it is done? So what we do is, to start with, we make an atomic model of the system to be studied. So just to give you the same example of propane, we take some propane molecules as starting configuration. This constitutes what is called a simulation box or simulation cells. For example, this can be considered as a simulation cell. Once you have this model, you write down the equation of motion for all the atoms in the sample. That is, you write down the Newtonian equation of motion. So, for example, for conservative systems, the equation of motion is mass times acceleration is negative gradient of some interaction energy. And then you solve the equation of motion numerically. So the input that you use in your computer is position of all atoms, that is r at time t equal to 0. This is what you have at r t equal to 0. And you also need the form of this potential, which is also called force field. You also need the initial velocities v at time t equal to 0. These can be determined by the temperature of the system. And when you solve the equation of motion numerically, as an output, what you get is position of all atoms for all times. That is, you get trajectories, or r as a function of t, where t is any arbitrary value, and also v as a function of t. Once you get these trajectories, then you can calculate various thermodynamic and structural properties of interest from these trajectories, because ultimately all the thermodynamic quantities and structural properties can be expressed in terms of RT and VT. Finally, as I alluded to earlier, we need to distinguish between two different types of simulation, molecular dynamics simulations, that is ab-initio versus empirical. So we agree that motion of atoms and molecules can be treated classically, but their interaction is governed by the electronic structure that can be treated accurately only in quantum mechanical formalism. So this means UI, that is force field, is to be estimated from quantum mechanical calculations. When this is done, the simulation involves both quantum mechanical and classical mechanics. So for example, force fields are described by quantum mechanics, and equation of motion calculations are done using classical mechanics. This approach is called ab-initio molecular dynamics, where ab-initio means from the beginning or without making any assumptions. Another cheaper alternative is to approximate the force field by a classical model, that is obtained empirically by comparison and fitting with experimentally measured data. This is empirical molecular dynamics. In this workshop, we shall focus exclusively on the empirical force field based molecular dynamics simulations of systems under equilibrium. With this, we come to the end of this module. Next, we begin the second module, where we see how to carry out an MD simulation, or in other words, how to make molecular movies equal to 0 or initial configuration. Then we'll talk about periodic boundary conditions. These are special conditions for avoiding artifacts due to surface atoms or molecules that we'll see. And then we'll talk about assigning initial velocities, that is v at time t equal to 0. After that, we'll talk about how to define the force field, because if you remember, the force field or the interaction between all atoms and molecules is one of the main components of molecular dynamics simulations. I hope that most of you must have seen the assignments in module 1, and from that you must have had some idea about statistical ensembles. We'll repeat that again in context of molecular dynamics simulations. After this, we'll talk about exactly how to solve the equation of motion numerically. We'll take a brief overview of velocity Verlet algorithm, which is a typical algorithm which is quite useful, and that is one of the most popular algorithms being used for molecular dynamics simulations. And then we'll talk about how to choose the right time step, how to store the trajectories, and after that, once you get the simulation done, we'll talk about how to process the data in post-simulation processing. So, preparing a simulation cell, that is obtaining R at t equal to 0. There are different ways of obtaining this initial system configuration. One way is making the system from scratch. When I say system from scratch, I mean starting with very few inputs. Of course, no one can build anything from scratch. As Carl Sagan once said, if you want to make a cup of coffee from scratch, you'll first have to create the universe. So you can start the system from scratch by using a .cif file with atomic coordinates obtained from experimental data. So crystallographers keep doing diffraction, X-ray neutron diffraction experiments on single crystals, and what they do is they obtain the atomic coordinates from these single crystals, and they store this information of atomic coordinates in a file which has an extension .cif, which stands for crystallographic information files. So if you have that file, you can use that as a starting configuration. Another way is to make a pseudo lattice for the system with arbitrary structure but known density. By pseudo lattice, what I mean is, for example, if you have a single crystal, it can have different types of crystal structures. But suppose you have a system, say you have water. Water might have a crystal structure. It has different structures for ice. But if you want to simulate liquid water, you can either use one of those structures, or you can make a pseudo lattice. That is, you just put water molecules at regular intervals, which has nothing to do with the real structure of water. But because you are interested in liquid structure, you can do that, and then when you simulate the system, they would ultimately take a random structure, which is ultimately what you want. Yet another way, actually this way is not very much different from this. If this is for mostly crystalline materials, for biomaterials like proteins and other things, you have a protein data bank where you can find the coordinates of some proteins, amino acids, and these coordinates are stored as .pdb files or sometimes .xyz files. So you can obtain these structures from protein data bank as well. Another way of obtaining the starting configuration is, of course, from a previous MD simulation. So for example, you might be running a simulation at different conditions of temperature. So for example, you do a simulation on a system at 300 Kelvin, and then you want to see what is the effect of temperature, so you want to do the simulation at 350 Kelvin. One way you can do that is you start with 300 Kelvin simulation, you get the output, and the last frame of your 300K simulation output you can use as the initial configuration of your next simulation at 350 Kelvin. Yet another way of obtaining the starting configuration is from a Monte Carlo simulation. This is a slightly different type of molecular level simulation. We cannot really talk about this in this workshop because this would be completely out of scope. But just for completion, Monte Carlo simulations can be used to obtain some structural configurations. For example, Monte Carlo simulations can be used to obtain gas molecules adsorbed in porous materials. So output from these simulations can be used as input for MD simulations. A little bit more about using .cif files. So .cif files can be obtained directly from crystallographic databases. For example, American Mineralogical crystal structure database is one such database. Then there's a crystallographic open database, and there are several others. If you want to find a CIF file for a material, you can probably just type the material's name and type CIF file for this, and you'll get some entries hopefully. Now these CIF files have atomic coordinates only for one unit cell, that is the smallest possible configuration that can be repeated. Even though, as we shall see soon, periodic boundary conditions render a unit cell infinite in all directions by making periodic images. So that means if you have one unit cell and if you apply periodic boundary conditions, you are actually making your system infinitely large. But even if you do that, even after doing that, the main simulation cell, that is the unit cell that you start with, should be as large as possible to capture all the complexities of the structure. Because if your unit cell is small and you make periodic copies of it, you might get an infinite structure, but the problem would be you are going to get periodic images of the same simple structure. We'll see, it will get clearer as we go forth. But the point is, if you want to have a large simulation cell and you have from CIF file you have coordinates only for one unit cell, then what you can do is you can replicate your unit cell a few times in all directions to obtain a supercell. So for example, this can be done by writing a simple code or by using a visualization software called Vesta. Then how to assign the initial velocities. Atomic velocities are determined by the system temperature, that is kinetic energy of the system can be written as half mv square, where these angular brackets mean average over different atoms. So if you take average over different atoms, put v square here, what you get is 3 by 2 kBT, where kB is your Boltzmann constant and T is temperature in Kelvin. So the point is, the velocities are ultimately related to temperature. If you increase the temperature, velocities will be increased, or rather vice versa. So at a given temperature T, the atomic velocities in an ideal gas follow a Maxwell-Boltzmann distribution. So to start with, atoms, molecules can be assigned velocities consistent with the Maxwell-Boltzmann distribution at the temperature being studied. Some people use a Gaussian distribution instead of Maxwell-Boltzmann distribution, which is technically not correct as far as ideal gases are concerned, but ultimately as the simulation progresses, this distribution gets adjusted to Maxwell's distribution on its own anyway. So this is not wrong either. Yet another alternative is to start the system from rest, that is v equal to 0 for all atoms, and ramp up the velocities. This means equivalently heating the system from absolute 0 to a given temperature. This results in a large initial fluctuation in temperature. So initially the temperature might shoot up to several hundreds of degrees, but eventually it would stabilize. The molecular trajectory during this initial period where you have large fluctuations is normally discarded, and only the trajectories after the system has equilibrated around the simulation temperature are used for calculating the properties. Now we have to talk a bit about periodic boundary conditions. So imagine a small simulation cells like this here. You see only one atom is in the interior all the other atoms are at the boundary. Now this atom which is in the interior feels attractive or repulsive, whatever forces, from all these atoms. Whereas for this atom, it feels interactions only with this, and this atom. So the number of interactions that this surface atom feels is different from the number of interactions that this interior atom feels. This means because of this surface, these atoms or molecules that are on the surface are going to behave differently from the interior atoms or molecules. If you replicate this 1 unit cell of argon, as you have seen earlier, into a larger supercell here, you can see the relative number of interior atoms has become very large, whereas the relative number of surface atoms is not so large. So the point is, small simulation cell size means a large fraction of number of atoms or molecules on the surface, and this could be problematic because, as we have seen, surface atoms behave differently from interior atoms. So to remove the effects due to these surface atoms or molecules, you can use periodic boundary conditions. Periodic boundary conditions are applied. What it means is, for example, suppose you have a simulation cell like this here with just 4 atoms. You make periodic copies of this original cell, one here, 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 here. All these are periodic images of the same cell, and you continue making these periodic images in all directions infinitely. So this is just a part of the infinite system. In reality, this extends all the way up to infinity in all directions. So this is called applying periodic boundary conditions. I don't know how many of you are familiar with this game of snakes. This used to be available in older mobile sets, or perhaps it is also available in the mobile sets today, but I don't know. This game makes use of periodic boundary conditions as well. We'll see how. Now, one consequence of applying periodic boundary conditions is that when a particle crosses a cell boundary, an equivalent particle enters the cell from the opposite boundary. So, for example, you can take a look at this cell. Imagine all these red atoms are either stationary, or if they are moving, they are not crossing the boundary. But the blue atom is crossing the boundary. So, in the periodic image, the cell looks like this at time t equal to 0. At time t equal to 1, the next time frame, this blue atom crosses the boundary. And so, here in this image, it has crossed the boundary, it has come here. But because these images are periodic, this means an equivalent atom has come here from the image below. So, if you just concentrate on the original cell, it looks like as if when an atom goes out from this side, another equivalent atom reappears from this side. So, coming back to this snake game, the snake grows larger and larger. So, if this is the tail of the snake, you can see it goes like this. It has come out from this direction, it has crossed the boundary, but it reappears here. And then it turns to this direction, crosses the boundary, reappears here, turns around, crosses the boundary, reappears here, and turns around, crosses the boundary, reappears here. So a large length of the snake can be represented in the same cell, although it is extended to a much larger scale. So this way, periodic boundary conditions can be used to depict the crossing of atoms across the boundaries. So when a particle crosses the boundary and it reappears at the opposite boundary, we can say the trajectory of that particle gets folded back. It is as if it goes out from here, gets folded back, and comes back here. This is a very important aspect of molecular dynamics simulations that we need to keep into mind, and we'll talk a bit more about this later when we talk about post simulation processing. So how to define the force field, and we once again bring our propane system back. So this is a cartoon of simulation cell of propane. All these white spheres are hydrogen atoms, the black spheres are carbons, and then they have bonds. So for a general molecular system, a typical atom can have bonded as well as non-bonded interactions. So for example, this hydrogen atom here interacts with this hydrogen atom in the other molecule, and this interaction is a non-bonded interaction, whereas the same hydrogen atom also interacts with carbon in the same molecule, and this interaction is a bonded interaction because there is a bond between the two. Whereas if you consider this hydrogen atom and this hydrogen atom, this is in a way a different type of bonded interaction, because here we are not talking about a straight bond. We are rather talking about a bond which is made up of an angle here and a dihedral angle here. We will talk about, we'll specify what a dihedral angle is in the next slide. But for the time being, the important thing is you can have bonded interactions or non-bonded interactions. So non-bonded interactions include the long-range electrostatic Coulomb interactions between charged particles and the short-range van der Waals interactions, in addition to special interactions in some specific cases. For example, four-body interactions or metal or external interactions. But in the present case, we won't talk about these details. And if you remember the assignment from the previous module, we talked about one very specific type of van der Waals interaction, that is Lennard-Jones interaction. So in general, the interactions can be written as a sum of bonded and non-bonded interactions. The bonded interactions would include interaction between atoms connected by a chemical bond. So for example, these two. These can also include interactions due to vibrating bonds, like say for example, this bond can be vibrating with its distance increasing, decreasing, increasing, decreasing. And then they can also include angles. For example, this angle can vary, so this can open and close, open and close, open and close. And then dihedral angles, we'll talk a bit in more detail about dihedral angles in the next slide. And there can be some more specific special interactions in some cases, for example inversion angle, improper dihedral angle, and so on, but we won't talk about them. So in general, interaction can be bonded or non-bonded. Bonded interactions can include bond distances, angles, dihedral angles. whereas non-bonded interactions can include van der Waals interactions and electrostatic Coulomb interactions. A bit more about bonded interactions. So, for example, as we said earlier, bonded interactions can include bond, that is, this distance can vary, and this type of interaction can sometimes be defined as harmonic interactions. For example, the interaction due to this bond energy can be written as half k Rij minus R0 square, where R0 is the equilibrium value of, or you can say the mean value of this bond length, whereas Rij is the instantaneous value of this bond length, and k is some force constant. Another type of bonded interaction can be that due to angle. So this angle can vary. For example, this, keeping this atom and this atom stationary, this atom can move up and down, and if it does, the angle would change. Similar to bond interactions, the angle interactions can be expressed as harmonic interactions like this, where theta 0 is the equilibrium value of this angle. By dihedral angle, what I mean is, imagine you have a 4-side object, that is, or you can think of a molecule made up of 4 atoms like this. This atom, you can imagine, is coming out of the plane of the slide. So, for example, this whole thing can be thought of being lying in the plane which is shown in yellow here. This bond is fixed, and then you have this bond which is going in the opposite direction, opposite to this. So this bond is lying in a plane which is shown in green. By dihedral angle, we mean the angle made by this plane and this plane. So dihedral angles can also, the interaction due to dihedral angles can also be expressed as harmonic interactions like this, where phi 0 is the equilibrium value. Coming to non-bonded interaction examples, as we have seen already in one of the assignments, one typical type of van der Waals interaction is Lennard-Jones type. This you have seen in the solution to the assignment is an interaction which has an attractive part and a repulsive part. It has a potential well which gives the equilibrium distance between any two particles. The electrostatic interactions or Coulomb interactions are given by this expression, where Qi and Qj are the charges of the two particles. They can be like charges or they can be unlike charges, but irrespective of whether they are like or unlike, this whole thing for a given system of two particles can be thought of as a constant. So what remains is a function that goes like 1 over r. So you can compare the behavior of Lennard-Jones for epsilon equal to 1 and sigma equal to 1, the red curve, and 1 over r, which is the behavior of Coulomb interactions. So one thing you can observe here is that whereas Lennard-Jones interaction go to 0 rather quickly by less than before r becomes equal to 4, the Coulomb interaction keep on going on and on without becoming 0. They have a finite value even for very large values of r. So that means Electrostatic interactions are long range interactions, whereas van der Waals interactions can be short range interactions. In fact, van der Waals interactions are short range interactions, whether we are talking about Lennard-Jones or any other type of van der Waals interaction. So, because they are short range, they are relatively cheap to calculate, whereas electrostatic interactions, because they are long range, they are expensive to calculate. And there are special methods of calculating electrostatic Coulomb interactions. One, for example, is called the method of Ewald sum. We can't really get much deeper into that right now, because that would be out of scope. But it is enough for you to know that Ewald sum is one of the methods that can be used to calculate electrostatic interactions. And because these interactions are quite expensive to calculate, if possible, if you are dealing with neutral systems, it is always better to ignore this interaction. Of course, it would depend upon your system. So, for example, if you're talking about polar molecules like water, you cannot really ignore electrostatic interactions, because each water molecule would have a charge distribution over itself, which is non-symmetric. In practice, the interactions are calculated for distances shorter than a cutoff distance. So, you cannot calculate the distance between any two given particles irrespective of how far apart they are. In practice, what you do is you take a particle, for example at 0, and calculate these interactions only for particles which lie within a sphere of a particular distance of this particle. That particular distance is called cutoff distance, and that distance should be smaller than half of the smallest simulation cell dimension. So, for example, if your simulation cell is a cubic cell 20 angstrom offside, your cutoff distance should be smaller than 10 angstrom. Coming to statistical ensembles, we define ensemble as a collection of microstates subject to an extensive constraint, and these are to be chosen for simulations according to the need. There are different types of ensembles. So, for example, you have microcanonical ensemble and VE ensemble, where you keep number of particles, that is n, volume, that is V, and total energy, that is E, you keep them constant, they are conserved. And this type of ensemble represents an isolated system. It represents an isolated system because the energy is conserved. That means energy is not transferred, energy is not exchanged with anything else. So, that means energetically you are isolating the system. And in reality, the only isolated system is the universe itself. But you're not, of course, you're not going to simulate the universe itself, because that would need infinite amount of computational resources. But this is, after all, a natural ensemble for MD simulations. What I mean by natural ensemble is that because energy is conserved, the Newtonian equation of motion are enough to if you what I mean is, if you solve Newtonian equation of motion, you get everything that you need to know about the system, because energy is conserved. In case energy is not conserved, that means energy is being exchanged with some other system, then you will have to add some terms to Newtonian equation of motion. We'll see that in the next ensemble. So, for example, the next ensemble is canonical ensemble or NVT ensemble. Here, number of particles, volume, and temperature are conserved, and this represents a closed system. By a closed system, you mean a system in contact with a heat bath. So, for example, you can consider something in a swimming pool, which is that something is is your system of interest, and it is in contact with the water in the swimming pool. So it is constantly exchanging energy with the swimming pool, and after some time, equilibrium is achieved between that object and the swimming pool, and the temperature of the system then remains constant. The temperature remains constant by exchanging energy with the heat bath, that is swimming pool in this case. If you want to simulate the system in addition to the normal Newtonian equation of motion, that is in addition to the force field, you need a thermostat term in that equation, and this is supplied by adding an artificial term in the equation of motion, and this is called thermostat, because by that term you are keeping your temperature constant. So experimentally, if you want to compare your simulations with an experiment, most of the times you would like to use NVT ensemble, because in your experiment you are keeping temperature constant, as I said earlier, the only isolated system is the universe itself. So all real systems are actually either canonical or other ensembles. The next one we can talk about is isothermal isobaric ensemble, that is NPT, and here number of particles, pressure and temperature are conserved. And just as NVT ensemble needs a thermostat, this also needs a thermostat, and in addition it also needs a barostat, which would keep the pressure constant in the simulation. There is yet another type of ensemble which is called grand canonical ensemble. Here you have chemical potential, which is mu, volume and temperature that are conserved quantities, and this represents an open system which exchanges not only energy but also particles with the surroundings. So this is more commonly simulated with Monte Carlo simulations, and this is the ensemble of choice if you want to study adsorption of gases or adsorption of molecules on some assembly of molecules or some porous materials. So with this we come to how to solve the equation of motion, that is the central part of molecular dynamics simulations. The objective here is to solve the equation mass times acceleration is negative gradient of some potential energy. Here we are not including the barostat or thermostat terms, just for simplicity. So we are talking about simulations in NVE ensemble for the time being. So this means given the initial position r at t equal to 0 of all constituent atoms, get the position of all atoms at all times r as a function of t. For this we consider Taylor expansion of a function. So imagine a function f of x. If we know the value of function at an arbitrary value of x, the question is, what is the value of the function at a value of x in the close near neighborhood of this value of x, that is x plus delta x. The way you can calculate or estimate the value of this function at x plus delta x with the condition that delta x is a very small increment in x, delta x tends to 0, is by making use of Taylor expansion. And Taylor expansion can be expressed in form of this equation. So f of x plus delta x is f of x plus first derivative of f with respect to x times delta x plus 1 over 2 factorial second order derivative of f with respect to x multiplied by delta x squared plus 1 over 3 factorial third order derivative of f with respect to x term, and so on. In general, the nth term is 1 over n factorial nth order derivative of f with respect to x delta x to the power of n. Now coming back to our problem, if we take position of an atom to be the function that we are interested in and the variable time is the variable x here, independent variable x here, then you can substitute r for f and t for x to get an expression of r at t plus delta t as r at t plus first order derivative of r with respect to t, which is nothing but velocity times delta t plus half second order derivative of position with respect to time, that is nothing but acceleration delta t squared, and so on. In the very beginning, when t equal to 0, you can substitute t equal to 0 here and you get this expression for r at a small increment of time delta t. So r at t equal to 0 is known from the initial configuration. V at t equal to 0 is known from the temperature of the system, as we had seen earlier. Accelerations at t equal to 0 can be calculated from the negative gradient of potential energy, but of course we do not know the higher order derivatives of position, so we can discard them because as delta t is very small, these terms are going to be even smaller and so they can be neglected. We'll take a look at a very popular algorithm which is called velocity algorithm now. So in this algorithm, what you do is, given that you know the velocities, positions and accelerations at time t, at any instant of time t, accelerations can be obtained from the negative gradient of the potential energy divided by masses. So from this information, you first calculate velocity at t plus delta t by 2. Notice that we are talking about delta t by 2 here, so that is, we are advancing the velocities to a mid step, not the complete step, and this can be obtained by this. We are neglecting all the higher order terms here, and that is okay as long as delta t is small enough. From this, you can calculate r at t plus delta t from rt and vt plus delta t. That is because r at t plus delta t is given by this expression, as you can see from the previous slides, neglecting higher orders of course, but Vt plus half At delta t is Vt plus half delta t. So you can resubstitute this value here to obtain r at t plus delta t in terms of Rt and V at the mid step. Once you advance the positions from t to t plus delta t, you can then calculate the accelerations from the new forces evaluated at this time instant t plus delta t using this expression, and then you can update the velocities by once again making use of Taylor expansion to this just first two terms of Taylor expansion. Mid step velocity from this step plus half of at plus delta t, which is, if you combine this equation with this equation, v of t plus delta t is obtainable as this. So once you obtain velocity at t plus delta t, you can calculate the kinetic energy, and from that you can calculate the temperature at t plus delta t from velocity at t plus delta t. So then the question is how to choose the right time step, that is delta t. And a good choice of the calculation time step delta t will optimize the performance by taking into account the following. Firstly, it should be small enough to capture the dynamics of interest. For example, if delta t is larger than a dynamical process, the simulations won't be able to capture that dynamical process. So for example, if you consider a diatomic molecule which is vibrating, and imagine it vibrates such a way that it completes one vibration every 1 femtosecond, which is 10 to power of minus 15 seconds. If your delta t is larger than 1 femtosecond, then you won't be able to see this type of vibration. Secondly, delta t should be small, but it shouldn't be too small. It should be large enough to be able to efficiently simulate a large enough amount of physical time. Now, typical physical time simulated are a few picoseconds, that is 10 to power of minus 12 seconds, for example, for capturing fast processes like molecular vibrations, to a few hundred nanoseconds, that is 10 to power of minus 9 seconds. And in some cases, you might also be interested in processes that occur at very large microsecond scales, that is 10 to power of minus 6 seconds, which is usually the case in biological systems. So depending upon what your system is and what your interest is, you need to have a different value of delta t. And for most purposes, given the current computational infrastructure, a femtosecond, that is 10 to minus 15 seconds, is often used as delta t. Now, a bit about storing the trajectories. You have done simulations, now you want to store that data. One thing about simulations is that apart from requiring large computational time, MD simulations also require large computational memory space. That is because typical output files can be a few hundred GB in size. So for example, the type of simulations I do, I normally end up getting output files which are of the order of 150 GB, 200 GB, of that order. This means it is useful to be economically choosy in storing the information, because for supercomputers you might get a large amount of computational memory space, but if you want to use your own machines, your own laptops for example, you cannot afford to store hundreds of GB of data for one simulation when you know you're going to do more and more simulations. One can in principle store positions, velocities and accelerations for all atoms at all times. That is, you store r at t, v at t and a at t for all t. But normally accelerations are not really required in most of the calculation of most of the properties are independent of accelerations. So unless particularly required, accelerations may not be stored. So this reduces the storage requirement considerably, because out of these three quantities, if you are not storing one, your system requirement immediately becomes 2/3 of the original requirement. And a further reduction in storage requirement can be achieved by skipping some time frames and storing time frames in finite intervals larger than the calculation time step. So for example, if your calculation time step is 1 femtosecond, instead of writing every femtosecond positions velocities, you can write every 10 femtosecond. So you start with r at t equal to 0 femtosecond, then you write r at t equal to 10 femtoseconds, then you write r at t equal to 20 femtoseconds, and so on. This can reduce your requirement considerably. What to do once you get your simulation done? That is post simulation processing. So the first thing to do after a simulation is to check for obvious contradictions in the resulting output files. For example, variables like total energy, temperature, pressure for NPT simulations should converge to stable values after initial fluctuations, because if you're simulating in MPT ensemble, for example, then your pressure should be constant. The initial parts of the trajectories where these fluctuations are large should be discarded and not used for calculating properties. So just for demonstration purposes, I'm showing here results from one of the simulations I carried out a few days back. This is a simulation of methane in a nanoporous silica material. The system is of course not so important right now. What is more important here is to see how total energy of the system changes with respect to time. And you can see the time plotted here is in terms of picoseconds. So this simulation goes from 0 to 2000 picoseconds, which is actually 2 nanoseconds. If you look closely, you can see that the initial total energy starts from here, it suddenly drops till here and bounces back and then tries to get stable. This is quite a stable trajectory. I would say this is extraordinarily stable trajectory, because you can see the variation in energy is really less than 1 part per million. This is when you have 372 molecules in the porous material, and this is when you have 500 methane molecules in the same material. You can see some slight changes. What is more interesting here is the behavior of temperature. So here you can see what I mean by fluctuations in a better way. When you start with the simulation, you can see there is a large fluctuation in temperature. Between any two time instants, the temperature can change from 100 Kelvin to 500 Kelvin, which is really large. And then as the simulation progresses, the temperature starts to get stabilized, and after about 500 picoseconds, it stabilizes to some value. Of course, there are fluctuations even after 500, even after 1.5 nanoseconds, but these fluctuations are more or less acceptable, because they are less than, I think, 10%. And how small the fluctuations you want in temperature would also depend upon what your interest is. So for example, if you are interested in a system which physically, in reality, which changes very quickly with temperature, then you need to have better sensitivities, and you would like to decrease these fluctuations even further. But for this system, this is okay. So what I would do in this system is I would discard the first 500 picoseconds of the trajectory and use only this part of the trajectory. Coming back to the energy fluctuations, just for your information, the energy fluctuations here are exhibiting exceptionally good behavior, that is because the initial configuration I used here was obtained from a Monte Carlo simulation, and that means the system was already equilibrated. But the most important thing for you to understand here is that initially the system parameters, energy, temperature, pressure, might show a large fluctuation, and then they should converge to a stable value, and it is the stable part that you should be using for analysis. Another point about post-simulation processing is, as in the experiments, the best outcome is achieved by dirtying your hands. What I mean is, if you are doing an experiment and if you treat your instrument as a black box, you just feed in something, you get something out, that is okay if your system is running well, but then you don't really understand much with this approach. What I would encourage anyone to do is to play with the instrument, try n different types of things, and the same applies for simulations. So in simulations, this means processing the molecular trajectories in different ways and sometimes calculating non-standard quantities by writing one's codes. So for example, if you are using a code like DL poly, which we are going to use, DL poly can act like a black box, and you can ask it to calculate some properties. It would just calculate those properties and give out those properties to you. You can analyze those quantities, but if possible, I would prefer to write my own codes for calculating the same properties, because that way I get to see how the trajectory is moving really. But if you want to calculate the quantities on your own, there is one thing that you have to keep in mind, and that is calculation of quantities using self-written codes or external codes even requires molecular trajectories in their unfolded state. And here I would refer you back to one of the previous slides where we were talking about the periodic boundary conditions. So remember these boxes from that slide. At t equal to 0, this blue particle is here, and in the next instant the blue particle crosses the boundary and it reappears here. This is the folded trajectory. So if you and indeed some MD simulation codes provide an option to write molecular trajectories in the unfolded state, but for most software, for DL poly for example, writes trajectories in folded state. That is, everything is limited within this box. Whereas for calculating properties, what you want is actually when this atom goes out, it should go out like this. So instead of folding back this atom, you would like to have trajectories which go out of the box. These are called unfolded trajectories. If you want to calculate quantities like displacement, for example, right? You cannot calculate the net displacement of an atom if you look at the folded trajectories, because the atom is moving in this direction. If you use folded trajectories, if the displacement of the atom would appear to be this much for folded trajectories, but actually the displacement is only this much, right? So that means you should be using unfolded trajectories. So in case your software doesn't provide unfolded trajectories, then you'll need some treatment for getting unfolded trajectories. So you treat the folded trajectories, you write a code which can give you unfolded trajectories from folded trajectories. And this is normally achieved in a post-processing post-simulation process, data processing, which unfortunately, because we have limited time, we won't be able to talk about this aspect. What we'll do is we'll take only those quantities which DL poly provides us. But in the future, if you really want to use MD simulations, I would recommend you to consider thinking about how the folded trajectories can be unfolded. And with this, we come to the end of this module. So this brings us to the last and third module. In this module, we'll see how to use MD simulation data to calculate some quantities which would make sense of the simulations. We'll cover in this module. We can divide the behavior of a system into structural behavior, so we can talk about structural quantities and dynamical quantities, which describes the dynamical behavior, how the atoms are moving, and in structural quantities tell you how these atoms or molecules are arranged with respect to each other. In particular, we'll talk about a radial distribution function and its Fourier transform static structure factor. In dynamical quantities, we'll talk about mean square displacement, velocity autocorrelation function, and power spectrum calculated from velocity autocorrelation function. And then all these quantities can be actually seen as some correlation functions. So we'll talk a bit about correlation functions in general. In particular, we'll talk about time correlation functions and the concept of time averaging and how Fourier transform of time correlation functions are related to experimental observables in different types of experiments. So radial distribution function. Suppose you have two types of atoms A and B in an isotropic medium. By isotropic medium, I mean it looks the same in all directions. Then the radial distribution function or the pair distribution function of the pair AB is the probability of finding an atom of type B at a distance r from origin, given that an atom A is located at the origin. It is denoted by this symbol or sometimes simply by this dropping AB. I need to mention that there are several functions like this which are quite similar to each other, but they have slight differences. So for example, the radial distribution function and pair distribution functions, they are quite similar, but they have a very subtle difference between them in that the radial distribution function gives is a quantity which depends only on the magnitude of r, whereas the pair distribution function or pair correlation function is the same quantity which depends on the vector r, that is, it also depends on the orientation. But for an isotropic medium, the two can be identical. To give you an example here, suppose you have an atom A here which is at the center. What you do is you move away from A and count the distance r. You can see that any given distance r would be a sphere here. So as r grows, the sphere grows, and as r becomes this much, you encounter another atom. So up to this point, there is no atom in the vicinity of A. So that means in that case, the probability would be 0. And then as you encounter this atom here, you'll see a peak in probability. And then for this distance, for slightly larger than this distance, there again won't be any contribution, or perhaps there might be, and so on. So you'll get a function like this. This radial distribution function in this way gives important insights about the structural arrangement of atoms or molecules in the system. So you can see how crowded or how sparsely populated these atoms are. So this can be an indicator of structural order in the system and thus distinguish between different phases of matter. So for example, crystalline materials would have a different type of radial distribution function as compared to liquids, and liquids in turn would have a different type of RDF as compared to gases. We'll see that later. And they can also be used to estimate the coordination number, which is an indicator of how optimal the packing is. That is, by coordination number you mean the number of atoms in the nearest neighborhood of a given atom. So here's an example of radial distribution function, and this example is from one of my works that dealt with propane confined in 1.5 nanometer pores of material which is called MCM41S. This is a silica material. What we did is we carried out simulations at 80 Kelvin for bulk and confined state of propane. By bulk state of propane, I mean the state where propane is not confined in anything as compared to confined state. And then for confined state, we had two different populations of propane, 137 molecules in the spore and 109 molecules in the spore. So we calculated the radial distribution function here. In particular, we focused on the central atom, central carbon atom of propane, and we calculated the radial distribution function for propane in bulk state and confined state, like this. You can see here. There you can see both the confined state radial distribution functions are quite close to each other. They are not quite different qualitatively, whereas the bulk state is qualitatively different. It has several very sharp peaks separated by nothing in between, whereas confined state RDF starts here and then it is more or less uniform for all the distances. So you can make a mental picture of how these molecules might be arranged. In the case of bulk propane, because you have peaks separated by nothing in between, it can actually represent an arrangement of atoms, something like this. So here you can see you start with this atom and start making spheres which grow larger and larger. In that case, you won't see anything up to this distance. After this distance, when the sphere has grown enough, these two atoms and these two atoms on this side would all fall on the same value of R. So you'll have a peak. After this, when the sphere grows larger, there would be nothing, and then it grows even larger. These two atoms are going to fall on that sphere. So you'll have a peak here again, and so on. So you can see that this is a very well ordered arrangement like that in a crystal. Whereas if you look at this RDF and use the same arguments here, the system looks something like this, which is a very disordered state. So what it means is, at 80 Kelvin, if you have propane in bulk, it behaves like a crystalline material, a solid, whereas when you confine it in these pores, it becomes like a liquid. And just to remind you, propane becomes solid if you cool it below 85 Kelvin in bulk state. That is an experimental fact. So, what this experiment and what the radial illustration functions calculated from MD simulations tell us is that if you put propane in the porous material, it remains liquid even at 80 Kelvin while it freezes when it is in bulk. Static structure factor is another quantity that can be obtained from the radial illustration function by a Fourier transform relationship. So you just take a Fourier transform of GR and after some manipulation, adding a number, you get SQ, and this SQ is experimentally accessible. Because this is experimentally accessible, you can calculate this function, static structure factor, from MD simulations and make a comparison of this function calculated from MD simulations with that measured from the experiment. So it is often used to validate a simulation by comparison with experimental X-ray or neutron diffraction experimental data. So if the match between your calculated and experimental data is good, that means your simulation is good. If it is not, then there might be some problems with the simulations, and if you have checked every other thing, most likely your force field, the empirical force field that you have obtained, that you have used in your MD simulations, might require some modifications, some tweaking of the numbers. So here's an example of MD simulation of fused silica. They used ReXFF based molecular dynamics, which is slightly different from the molecular dynamics we are talking about here. In particular, ReXFF based molecular dynamics can help you trace chemical reactions, which we are not using here, but just for an example, you can see that MD simulation data can be compared with the experimental data. Here they have neutron diffraction experiment data represented as symbols and MD simulation data represented as lines. Coming to dynamical quantities now, one such quantity is mean square displacement. So as the name suggests, mean square displacement is the square of displacement of atoms averaged over all atoms of interest and at all time origins. This averaging over all time origins is quite important, and what it means is, just like when you average over different atoms, what the quantity that you get then becomes independent of which atom you're talking about, because this is an average quantity. It is the same for this atom, for this atom, for this atom, for this atom, for all the atoms. Just like that, analogously, when you talk about time averaging, what it means is all times are equivalent, all time instants are equivalent. That is, there is no special time, and that in turn means there is no t equal to 0, all right, or in other words, you can look at the molecular movie starting from t equal to 0 in your simulation, or you can look at the movie at any other instant of time and it would still behave the same. We'll talk a bit more about averaging over time origins. It is quite important that you understand this, but we'll talk about that later. For the time being here, just understand that when you calculate mean square displacement, you are taking time origins in addition to averaging over time origin, in addition to averaging over the number of all atoms. And this dual averaging is normally denoted by this angular brackets. So here you are taking the difference between the position of an atom at time t and at time t equal to 0 in the simulation, squaring it, that is square displacement, and then you are taking a mean. So this is mean square displacement. Now, together with Einstein relation, it can be used to estimate the self-diffusion coefficient of the system. So, self-diffusion coefficient of the system can be obtained by making use of this equation here. So, what you do is you find out the mean square displacement, and if you divide that by twice ndt, where t is time and nd is the number of degrees of freedom, or in other words, the number of dimensions your atoms are moving, then it gives you d self with the condition that t has to be very, very large. So, just like calculating the mean square displacement for atoms, you can find out, if a molecule is made up of several atoms, you can find out the center of mass of the atom, and you can calculate this quantity for the center of mass of the molecule. In that case, instead of giving information about how atoms are moving, it gives you information about how the molecule as a whole is moving. And log-log scale plot can reveal dynamical behavior. So, if you remember from your last assignment, log-log scale plot can show some very interesting features as compared to a linear scale plot. So here we have MST plots in the two scales, linear scale and log-log scale, for a system of 4 fluids inside ZSM5 nanoporous material. So this nanoporous material has channels. These are the pores represented here. They have a very intricate network of pores, 5.5 angstrom in diameter here. You have straight channel pores and zigzag channel pores in a plane perpendicular to the straight channel pores. We have 4 different fluid molecules here: propane, acetonitrile, acetaldehyde, and acetone. And as you can see, mean square displacement of these fluids as a function of time is different. For acetonitrile, this is a really low value. For acetaldehyde and acetonitrile, it is relatively larger. And for propane, this is really large because you can see there is a break in scale here. So it is growing really, really fast as compared to all of these together. So what it means is that mean square displacement of propane grows very fast with respect to time. So if you just take a slope of this part at time t tending to infinity, that is at larger times, if you just take a slope of this curve, MST against time, the slope gives you this quantity, and you just divide that by 2nd, you get the self-diffusion coefficient. If you make a log-log plot of MST, what you get is something like this. And this can tell you how the molecular motion is changing its behavior in time. So, for example, initially all of them exhibit an increase in mean square displacement with respect to time, which is more or less similar. And if you remember from your last assignment, when you use log plots for a power function, a power law, the slope of the plot can tell you about the exponent. So this behavior tells us that mean square displacement is proportional to time squared. So remember, we are talking about mean square displacement, and if it is proportional to time squared, it means the displacement itself, that is square root of this, displacement of this would be proportional to square root of t square, which is time itself. So displacement is proportional to time, and this happens in any rectilinear motion, right? Whereas as time progresses, mean square displacement starts to increase relatively slower with time. So here, for example, you can see mean square displacement is proportional to t, and this is in fact what is called diffusive motion, when mean square displacement is proportional to time. So you can distinguish between two regimes for propane. When mean square displacement is proportional to time squared, or displacement is proportional to time, which is rectilinear motion, and the diffusive motion here. So it starts with rectilinear motion, goes to diffusive motion. For other molecules, it is even different. For example, in this region, all these three different molecules exhibit a mean square displacement which is more or less constant in time. It doesn't increase at all, and that is as if remember, mean square displacement here in this case is not increasing, but it is not zero. So that means there is still some displacement, but it is not increasing. So you can make a mental picture of how these molecules are behaving. Imagine all these molecules as these spheres here. So suppose you start your movie at t equal to 0 like this, and then you put on the movie. When you put on the movie at t equal to 0, all these atoms start moving. Initially, when this atom moves, at least for this much distance, its motion will be rectilinear because it won't encounter any other molecule in its vicinity. So this is represented by this part, right? And as you can see, this lasts for a really small time, 0.2 picoseconds, you can see here. Whereas as time progresses, for propane, it encounters collisions which slows it down, and what you get is diffusive regime here. Whereas for these other molecules, what happens is this atom gets surrounded, or this molecule rather gets surrounded by these molecules, and it keeps agitating within a sort of cage formed by all these surrounding molecules. This is called the caging regime, where the molecule is agitated but it is unable to get out of this cage because made by the neighboring molecules. After some time, it is able to break this cage and come out, and then it gets into trapped into another cage, agitates there and gets out, and so on. So at very long times, you can see the motion would again look like diffusive motion here. So in general, you can see there will be three different time regimes of motion. First, the rectilinear or ballistic regime, and then there would be caging motion, and then there would be a break in the cages, and then it would go on to diffusive motion. This is more or less the general behavior, and the caging regime in particular is seen for most of the glass materials, whereas for simple liquids like propane, no caging regime is normally seen. You just go directly from ballistic to diffusive regime. Another quantity that is quite important, especially for biomolecules, is root mean square deviation of atoms. This is slightly different from mean square displacement, or this is not root mean square displacement, this is root mean square deviation of atoms. So what it means is, normally MD simulations try to get the structure of a protein molecule, and to get the right structure, what they do is they take a reference molecule and the model molecule, and then try to find out the difference between the atoms of this molecule under study and the atoms of the reference molecule, which is always stationary. Take this square, divide by multiply by the mass of each atom, divide by the total mass, and what you get is a quantity which is RMST. So here, for example, there is an example of molecular dynamics study of fibrinogen with zeolite nanoparticles. So fibrinogen, for your information, is a protein complex that is made in liver, I think, and it is responsible for clotting of the blood. So they wanted to see how this protein complex interacts with zeolite nanoparticles. And this protein complex has a complex structure. It is made up of two D domains connected to an E domain. So the regions of this protein complex are divided into different regions. You have two blobs on either side of a central blob, which are connected by very thin thread like molecules, and the blobs on either side are called D domain. The blob at the center is called E domain. So they wanted to see how this protein complex interacts with zeolites. So they kept this molecule, this protein complex, in contact with the zeolite nanoparticle, and then they compared the root mean square deviation of the atoms of this complex as a function of time for free D domain and for D domain which is placed close to the zeolite. So you can make a comparison and see how the zeolite affects the motion, for example, of the atoms of this molecule. Another quantity which is similar to this one is root mean squared fluctuations. So the only difference here is that this is a function of time, and we are taking an average over all atoms here and finding their evolution as a function of time. In this case, on the other hand, you are taking an average over time for each atom and finding out how each atom of this domain, okay, um, is is fluctuates with respect to the reference. So you can see that all these domains are in turn made up of residues, molecular residues, and here you can see all these residues have different amounts of root mean square fluctuations. So this would give you an idea about which of these residues are more mobile, for example, as compared to the others. This type of analysis is quite usual for biomolecules and people who are studying biophysics. They do this type of analysis. You can read more about this in this paper. So another quantity which gives you information on the dynamics of atoms or molecules is velocity autocorrelation function, or VACF. Again, as the name suggests, VACF is the correlation of atomic velocities at an instant of time with themselves at t equal to 0. That is, you calculate the velocity of any atom at time t, and take a dot product of this velocity at time t equal to 0, take an average over all molecules over all times, and what you get is this. So this tells you how velocity at any instant of time t is related to the velocity at t equal to 0. Just like in mean square displacement, there is a Green-Kubo relation here, which can be used to estimate self-diffusion coefficient of the system here. In fact, one can show that this relation, Green-Kubo relation, is equivalent to Einstein relation for mean square displacement there. And again, just like mean square displacement, it can also be calculated for center of mass of the molecule. If you take a Fourier transform of the velocity autocorrelation function, don't take this to think that you are taking a Fourier transform of this equation. What I mean to say is you take Fourier transform of just this part, that is velocity autocorrelation function, you'll get a power spectrum. And we'll talk about power spectrum in the next slide. So here just an example of a velocity autocorrelation function. You have seen ZSM5 nanoporous material in the last slide. Here we have a comparison between the behavior of propylene molecule trapped in ZSM5 nanoporous material and the same molecule trapped in NaY zeolite, which has a structure which looks something like this. It has relatively larger cages. These are 11.2 angstrom in diameter as compared to 5.5 angstrom in diameter here. So you can see velocity autocorrelation function decays and then it fluctuates and then it stabilizes to 0. You can see a major difference between the behavior in ZSM5 and NaY. So for example here in ZSM5 there is a lot more oscillations before the function dies down. One thing you can see is this is ultimately this gives you the relation between the velocity at any instant of time with the velocity at time t equal to 0. So at time t equal to 0, the velocities are both equal. That is, if you take t equal to 0, here it becomes v of 0 dot v0, which is ultimately v squared at 0, which is this quantity. As time progresses, the two velocities are more and more different. So this correlation decays. And after some time, what happens is, so initially this molecule is starting to move, just like in mean square. When we talked about mean square displacement, we talked about how the motion evolves here. So initially this is rectilinear motion, and the velocity is almost like a straight line velocity. It doesn't change its direction. It might change its magnitude, but it doesn't change its direction. And then this molecule encounters another molecule, maybe this or this or this or this, one other molecule, and it collides with it. When it collides with it, it is going to change the direction of its velocity, and sometimes it might just recoil back. So that means the direction of velocity has changed. So v at t now has a different sign as compared to v at 0. So that means when you take a dot product here, what you get would be a negative number. So that means the correlation goes to negative, and then goes up again. So this is the negative region is called the recoil region. It just tells you that there is a lot of going back and forth by the molecule. It goes out, collides with another one, comes back, and so on. And this is, the motion is more agitated in ZSM5 as compared to NAY. That is because the pore dimension here is much smaller. So the system is more crowded here. So you would encounter a lot many more number of collisions as compared to here. So this is just to give you an idea how you can calculate different quantities and how you can interpret them to get an understanding of the system. As mentioned in the last slide, you can take Fourier transform of the velocity of correlation function, and that gives you a power spectrum. You might find that this is a different representation of Fourier transform, but actually when you take a Fourier transform, you are talking in terms of complex quantities. There could be a real part and there would be an imaginary part. What we are talking about here is the real part. So you remember, the real part is cosine term, the imaginary part is sine term. So we are not talking about the sine term here, we are talking about the real part, cosine term here. So this is a Fourier transform, real part of velocity over correlation function, and you can denote this as I of omega. So coming back to the last assignment, I asked you to find out between Fourier transform duals of momentum and position and time and energy. So time and energy form one such dual, and using Fourier transform you can convert a quantity in time to a quantity in energy. But omega is of course frequency, but ultimately it is related to energy, because if you just multiply this by h cross, where h cross is reduced Planck constant, you get energy. And this power spectrum corresponding to the velocity over correlation function can be obtained in an inelastic neutron scattering experiment, for example. So coming back to our previous example of propane in nanoporous silica MCM41S, we see that the power spectrum for bulk state again looks different from confined state. And you can go back to the slide on RDF functions, and you can see the change in the behavior going from bulk to confined here is quite similar to the change in the behavior of RDF that you see from going from bulk to confined behavior. So for bulk state you have a spectrum which has clear distinct peaks here, whereas for the confined state all these peaks merge into each other and give rise to just a very broad single peak. So this is just as we saw there was disorder in the structure of propane when it is confined to this material. You can see there is a disorder in the vibrational behavior too, right? So now we can talk a bit more about correlation functions in general. Time correlation function. So generally, time correlation function Ct between two variables At and Bt is defined as this quantity. And here I would like you to spend some more time in trying to understand what it means when I say time averaging. So here we are taking a time average of these quantities. I'm assuming that these quantities are averaged over all different atoms or molecules already. So here we are focusing exclusively on time averaging. What you do is you take a starting time t0, find out A at that time, take next time t0 plus t, find B at that time, and then take their product. After that, what you need to do is you take an average over all t0s. That means you first find out the sum of all t0s here and then divide by tau, which is equivalent to integrating this with respect to dt0 as t0 goes from 0 to tau and then divide by tau. This would become a bit more clear when we talk about this table here. So imagine you have collected a trajectory, molecular trajectory, and you have taken an average over all molecules, and now you have just 5 time frames in your trajectory. In reality, when you do MD simulations, these numbers would go to millions, but right now, just for simplification, we are talking about just 5 time frames. So if you want to calculate the time correlation function between these two quantities, you start with calculating this function when t equal to 1. When t equal to 1, what you do is you take t0 as 1, then t0 plus t becomes 1 plus 1, that is 2. So you get this pair here. Next, you take t0 as 2, then t0 plus t becomes 3. You get this pair. Similarly, for t0 equal to 3, you get this pair. t0 equal to 4, you get this pair. So you get all these pairs when you change your t0. Okay. And by time averaging, what you mean is you take an average over this quantity, take average of this product over all these time frames. Similarly, if you want to calculate C at t equal to 2, what you do is you take t0 as 1 and t as 2. So 1 plus 2 gives you 3. So you get this pair. When you take t0 equal to 2, you get this pair. When you take t0 equal to 3, you get this pair. If you try to make t0 equal to 4 in this case, 4 plus 2 is 6, but you do not have the trajectory at 6 time frames. So you just stop here. Similarly, for t equal to 3, you'll have to stop here. For t equal to 4, you will have just one entry here. And taking an average of just one entry means you're taking that entry itself. So we haven't included that here. So just to summarize, for t equal to 1, you'll take an average over all these numbers. For t equal to 2, you'll take an average over all these numbers. For t equal to 3, you'll take an average over all these 3 numbers. This is what is meant by time averaging. So if A is equal to B in this case, it becomes autocorrelation function and is sometimes written simply as A0 of t. Because here we are as I said, when you have taken an average over time, it means you have removed any speciality on any instant of time. So all instants of time are equivalent. So that means t0 is arbitrary. T0 can be anything. So if T0 can be anything, why not make it 0 and make it simpler? So, so you can write the autocorrelation function as this here. And as you have seen already in the case of velocity autocorrelation function, it gives you a visual understanding of dynamics, how the correlation starts from a large value and then it decays, the correlation decays and then it goes to 0. And time integrals of Ct are related to macroscopic transport coefficients. So for example, in this case of velocity autocorrelation function, you have already seen, you can go back to that slide and see, you have already seen that you have Green-Kuber relation which relates the time integral of velocity autocorrelation function to the self-diffusion coefficient. And Fourier transform of Ct are related to experimental spectra. Again, for velocity autocorrelation function, you have seen this. When you take Fourier transform of velocity autocorrelation function, what you get is a power spectra or vibrational spectra, and then that can be compared with experimental spectra. And one last important point is to understand that a consequence of time averaging is that the statistical quality of Ct data worsens progressively for longer times. What I mean is, initially when t equal to 1 and you want to take time averaging, you had 4 different entries here and the averaging would be good. In the next instant, you have just 3, 1 less than here, just 3 numbers here. So when you take an average, this average would not be so good as this average, and the statistical quality therefore would keep on getting worse and worse as you go in this direction, as you go for longer times. So this means if you are calculating, sorry about that, this means if you are calculating autocorrelation functions or any other correlation function in general from your MD simulation data, if your MD simulation data goes for say 2 nanoseconds or 2 million steps, I won't really take the value of correlation function at 2 nanoseconds very seriously, because it would be really badly averaged. I would just take the correlation function up to say 1.5 nanoseconds seriously. So as I said, Fourier transforms of time correlation functions are related to experimental observables. So for example, if you take autocorrelation function of atomic velocity, as we have already seen, and you take the correlation function is this, you take Fourier transform of this, it can be compared with inelastic neutron scattering spectra. If instead of velocities you take a unit vector along a permanent dipole, and you take Fourier transform, it would be equivalent to this dielectric relaxation spectroscopic spectra. And I think at least one of the participants is familiar with this experimental technique here, so they might find it interesting. In case you don't have a permanent dipole, you might have a transient dipole, And if you take a correlation function of that, take a Fourier transform, you get IR spectra. And if you take a second order Legendre polynomial of this correlation function, here you make this correlation function instead of this, what you get is a Raman spectra. Instead of talking about dipoles, unit vectors along dipoles, if you take angular velocity about center of mass and take this correlation function, take its Fourier transform, you get far infrared spectra. And X component of magnetization would give you nuclear magnetic resonance NMR spectra. In fact, unit vector along a dipole or along any molecular axis can also be used to calculate a correlation function, which is accessible with NMR relaxometry, sorry. But we won't talk much about that for brevity. So with this, we come to the end of this talk, and I hope you might have got some decent idea about how to do molecular dynamic simulations and how to use them, more importantly. But before we close, here are two assignments I have designed for you to practice your knowledge that you might have gained so far. The first of these two assignments is about the Lena-Jones potential energy function. It is a lot easier to understand a function when you try to plot it. So the assignment is about plotting this function and thereby trying to gain an understanding of how this function varies. Similarly, the second assignment is also about plotting a function, this time an exponential function, decay function, which is very useful in spectroscopy, for example, and in several of the various fields. So I hope with these assignments you'll get a better understanding of how these functions behave, and that is the idea about this assignment. Once you do that, and if you are interested, you can read further some of these references. So, for example, the very first one here is a paper I had written in 2017 with some colleagues. This is a review paper, and here we specifically talk about how NMR spectroscopy and neutron scattering can be combined with molecular dynamics simulations to understand some geofluids, for example. The second paper, similarly, is a very brief overview of molecular dynamics simulations. So you'll find all the information that we have covered in this talk in this paper. It's a very simple, very easy to read paper. I would highly recommend you to go through this. And then just as these first two papers give you a very brief overview of MD simulations, if you want to dig deeper and if you have time, you can always consult standard references, standard textbooks. For example, one is by Frankel and Smith that was published in 2001, and the other one, the classic computer simulation of liquids book by Allen and Tildesley. So with this, we come to the end of this talk, and I would like to thank you all.